Okay, example 2. Scientists have found certain tree resins that are deadly to termites. To test the protective power of resin, protecting the tree, a lab prepared 16 dishes with 25 termites in each. Each dish was randomly assigned to be treated with 5 milligrams or 10 milligrams of resin. At the end of 15 days, the number of surviving termites was counted. Assume that termite survival tends to be normally distributed with both dosage levels. Is there a statistically significant difference in the mean number of survivals for those two doses? Now here, I think it's worth just sort of discussing what will be our x and y. So our x might be the 5 milligram population, and our y might be the 10 milligram population, right? So the n sub x, some people might think it's the 25 termites, but no, actually there's 25 termites in each of 10, I assume, Petri dishes. And so really there's 8 Petri dishes that have been randomly treated with 5 milligrams and 8 that have been treated with 10 milligrams, right? So this is 8 and 8. And when we say 8, we mean the dishes of treatment. And the termites aren't the subject. They aren't the cases that we're interested in. The termites are sort of the test, right? You could get 25 termites surviving, or you could get 0 surviving, right? So how many termites survive? That's our dependent variable. Okay. So let's see. Well, one thing we could do is start off with our hypotheses. Our null hypothesis is that these two dosage levels are roughly the same, right? So we might say something like the mu sub x bar minus y bar would just equal 0. They're the same. That's what that means. The alternative is that they are not the same. Maybe that one is more powerful than the other, and we don't know which one. All right. And we could easily set our significance level to be 0.05. And now let's talk about the actual setup, the decision stage. So in the decision stage, let's see what we have here. Well, we've set up this 0.05 level rejection. And we could just go ahead and put in the 0 for, this is the x bar minus y bar. But what would be the t? Well, the nice thing about this being 0 is that the t as well as, the t distribution as well as the x bar minus y bar start off the same, but they're not going to have the same numbers out here. Okay, so that's why we do have to put them on different lines. They're still talking about different things. Okay, so let's talk about the t values. And before we do, it might be helpful to figure out the new degrees of freedom. So the degrees of freedom of differences will be 7 plus 7, so that's 14. Here we can do hypothesis testing, just jump in right away, because we can assume, because it's given, that termite survival tends to be normally distributed within these two dosage rates. Okay, so if you go to example 2, you'll actually see the date. Oh, sorry, 1 second. Okay, you'll actually see the data here. Right? And so here we see dosage. So here's the 5 milligrams as well as the 10 milligrams. And here are the survival counts. So how many termites survived? Notice that there's no survival count over 25. 25 is the maximum you could have. But even the highest tends to be something like 16. The lowest survival count can't go below 0 because you can't have negative termites surviving, right? So here we have the survival count. Okay, so let's see what we have here. Can we figure out what the the critical t is? So I'll put critical. Can we figure out what the critical t is? Well, I think we can. let's see. Why don't we use, you could use the book. I'm going to use Excel to find the critical t. So I'm just going to write for myself step 4, so I remember where I'm at. Critical t. I know that my, I know the probability, two-tailed probability that I need, 0.05. And I know my degrees of freedom, which is 14. So I see that the critical t is the same as before. And that's because we use the same two-tailed probability and the same degrees of freedom differences. And so here, we know that it's negative 2.14 as well as positive 2.14. Great. So what we can do is now from here go on to looking at our actual sample. So I've run out of room there, so I'm going to do most of it here. So let's talk about, oh, this is actually step 3. It's part of our decision stage. So step 4 is now actually talking about the sample. So it would help to find the samples mean difference. So that's going to be the average of one of these, of x, minus the average of y. And we want to know, is this difference going to be significantly different from 0? We can't just look at the raw scores because we need to figure out how many standard errors away we are, right? And so how should we find the standard error for the difference? Well, that's equal to the square root of the variance of x over n sub x plus the variance of y over n sub y. So let's find the variance of x over n sub x and the variance of y over n sub y. Let's do that. So the variance of x all over 8 and the variance of y all over y, of 8, right? Okay, so we see that the variance for y is a lot different than the variance for x, right? And that's helpful for us to just look at briefly right now, just because this will probably give us an idea, well, the variance of these samples are so different, we probably don't have a good reason to pool these two together, right? We don't have a good reason to assume that the populations are similar. So remember, when you're not sure, when in doubt, go with non-homogeneous variances. Just assume that they're different. Once we have that, then we could find the square root of adding these two standard errors together. And we get 2.5, right? Once we have all of that, then we could find the samples mean difference t, right? So the sample t, right? And that would be, I'll just write sample t. And that would be the sample's mean difference minus 0 divided by the standard error of the S dot, right? And so what would that be? Well, that would be this guy, and I'm just going to leave out that subtract 0 part, divided by the standard error. And we get 2.15. Ooh, we're close. But it is still more extreme than 2.14. So it doesn't have to be extreme in the negative end. It doesn't have to be extreme in the... It could be either extreme in the negative end or extreme in the positive end. This is extreme in the positive end. It's just right outside our border. And let's find the p-value. So in order to find that p-value, we use t distribution, because we have the t-value that we want, the degrees of freedom, and we want it to be a two-tailed p-value. So it's going to add up this little chunk and this little chunk together. And that's going to be 0.049. So right under that, so we'll just skip to step 4. Our p-value equals 0.0449. That is right just a hair underneath our alpha of 0.05, right? But it is underneath, and so we would probably reject the null. Great. And finally, example 3. 2 months before a smoking ban in bars, a random sample of bar employees were assessed on respiratory health. 2 months after the ban, another random sample of employees were assessed. Researchers saw a statistically significant increase in the mean scores of health. P equals 0.049. We had an example of that, two-tailed. Which of the following is the best interpretation for this result? Well, let's think about this. The probability is only 0.049 that the mean score for all bar employees increased from before to after the ban. Is that what this means? Well, for me, it helps to draw that S-dot, right? And it's saying, so the null hypothesis would be that they would be the same. Like before and after, it'd be exactly the same. But what they actually found is that there's some extreme value. But they said increase. So there's an increase in mean scores. So there's a positive difference, let's say, from after minus before, right? So there's been this increase, right? So it's somewhere actually up here. That increase tells us that, right? And it's P equals 0.049. So we could actually draw this pretty carefully. It's just right above that cutoff, right? Does that probability show that only 0.049, there's only 0.049 probability that the mean score for all bar employees increased? That's not what this means, right? It's not saying that there's only a small chance that it increased. It's actually saying there's a pretty good chance that it's not the same, right? Or there's a pretty small chance that it's the same, right? That's really what this is saying. So this one we could just rule out. Another possibility is that the mean score for all bar employees increased by more than 4.9%, right? Does this actually talk about does p-value actually talk about the raw score on respiratory health? No, it doesn't really talk about that score at all. It's the probability of finding such a difference. So it doesn't have anything to do with the actual scores. So what about this one? An observed difference in the sample means as large or larger than the sample is unlikely to occur if the mean score for all bar employees before and after the ban were the same. So this actually has some things we could use. So this is about considering that all the bar employee, the mean score for before and after are the same. That's important because that's what the SDOM actually represents. That's what this p-value is actually talking about. Something about this idea that before we considered, what would we get the sample if we considered that they were just the same? And this is saying an observed difference in sample means as large or larger than the sample, is very unlikely to occur. It's only likely to occur with 0.049% if the mean score for all bar employees, the true score, is actually the same. So this is actually a pretty good contender because it's talking about the S-dot. It's talking about how 0.049 means it's very unlikely. It's a small percentage, right? So this I would leave as a definite contender. Maybe there's a better answer. I don't know. There is a 4.9% chance that the mean score of all bar employees after the ban is actually lower than before the ban. So this is saying there's a small chance of the opposite hypothesis being true. Well, that's probably not the case. But it really, it sort of depends on what the null hypothesis was. But really, this the null hypotheses in a so the null hypotheses in a two-mean hypothesis test is usually that they're the same, not that one is less than the other, right? We don't usually do that. So this, maybe there's a way that it could be true, but is probably not true if we did hypothesis testing at all. And then only 4.9% of the bar employees had their score drop, while the other 95.1% had their scores increased. This would be a correct interpretation if we weren't talking about the S-DOD. If this wasn't a reflection of the population, then maybe that would be true. But this isn't talking about a population. It's talking about the S-DOD. So this is actually a wrong interpretation. So the correct answer is C.